Hello, everyone. Thank you very much for the nice welcome, Tim. So my name is Robin. I'm from TU Munich. I work at the Munich Institute of Robotics and Machine Intelligence. And my background is from the human-robot interaction point of view. So I come from the field of industrial manipulators, and everything I will be talking about kind of refers to this manipulator problems. Exactly. So I want to today focus a bit on the challenges of human motion prediction for actually certifiable safe applications. So I come from the TUM MIRMI, as I said. It's the AI Robot Performance and Safety Center, which we have founded there for the last 6 years, together with Professor Haddadin, now being led by Lorenzo Mazia and Achim Lilienthal. And in this lab, what we do is we kind of take an overall perspective on how can we make robotic applications safe using injury knowledge, biomechanical assessments, robot motion control, and safe control. And we have a lot of partners, a lot of projects involved in this laboratory, which all kind of focus on one thing. They are all usually industrial applications where we have flexible physical interactions that are required. We have humans in the loop. We have undefined path planning. We have objects with various geometries. And our big point is, how can we actually safely integrate intelligent robotics into these factories for such applications? For that, we have built an infrastructure at the MIRMI, and this whole infrastructure evolves around having harm evaluation, performance testing, implementation areas, integration testing areas. And that whole place is supposed to be used for then also creating certified safe applications in the end. Now, certified safe applications, if I'm talking about certification of robotic applications, there is some very fundamental steps that we always need to follow and always need to keep in mind. First is that we always have to have a look at our intended applications, and we have to run through a whole loop in order to, in the end, have something that we can call certifiably safe. The first step is that we have to look at what is the limitations of my machinery. So what is my robot actually capable of? What can it do? The second step is that we have to identify scenarios. So what is the situation that we need to consider? Is there a robot moving around in the human area? Is the human moving towards the robot? Is it moving away from the robot? Is there constraints? What is the context? Then, if we know the scenario, we can identify what is the hazards that are actually related to the scenarios. So what we look at here is the severity of harm. So what kind of injury can occur in case the robot hits the human? How likely is that? How well is that avoidable? And then there's obviously two options. We can say, okay, it's safe, no injury happening, all good. Or if it's not accepted, we have to go into the cycle of risk mitigation strategies. There is what we are looking at mostly safe impedance control or collision reactions or velocity scaling or the such. If there is somebody who knows a lot about standardization, you might be familiar with also the terms of power and force limiting and speed and separation monitoring. That is, it doesn't look like it. Then that's great, because I will not refer to these terms at all, even though they're part of standardization. So if we have run through this loop, if we've documented everything well and have really taken care of considering the state of the art to make this application safe, we can get a certification on this safety. What does this certificate mean? This certificate means nothing but that I have, based on the state of the art that is currently available, done everything to reduce systematic errors that can cause harm to the human. There is always a remaining risk for random errors occurring that is accepted and based on some severity of harm versus the exposure to the potential hazard occurring. And for robots and robotics applications, this is defined by a standard that refers to this application with the robot always being very severely hazardous, ending up with an allowed failure rate of 10 to the -7. So if we ever want to certify something for robotics applications, currently the failure rate of whatever you have is allowed to be 10 to the -7. And it has to be implemented by 2 channels. So there is, for all of these sectors, for human-robot interaction, the limitation of the machinery, the risk mitigation, the hazard analysis, there is, well, reasonably good standards and reasonably good options to really do this certification or to perform this certification. Where we struggle a lot is the part with scenario identification or risk identification. Here, we only currently have like one very valid option, which is the ISO 12100, it's called. This ISO 12100 gives a specific procedure on how to perform this risk assessment, and it's static. Like after you've performed the risk assessment, this is what it is. For example, I would consider a human-robot interaction where the robot has a screwdriver and the human can come close with his hand, and I have to then define areas where the hand can be constrained. Then I have to move according to this constraint. I can define an area where the human is unconstrained. I can move according to this constraint, but I cannot currently flexibly really change these options. The only thing that we can currently do based on the standardization is presence detection by like using laser scanners. So if there is a human, I have to kind of stop or go for a slow velocity. That is a bummer, a bit limiting. Because what we have seen in our research and what we have really discovered in the last years of performing injury testing, once again, referring to applications, human and robot are close to each other. We are trying to estimate the positions of the whole arm or different body parts. And for this interactions for the between a robot and a human arm, for example, what we have observed is injuries, for example, happening in unconstrained collision situations. We've built test stands and run like thousands of tests by now. Or what happens if we have collisions in unconstrained scenarios where the human cannot move away. What is the differences? We, by these tests, have been able to generate some thresholds for energy levels that are allowed in different situations, and that could be allowable. And now if we would look at this static way of currently doing a risk assessment, which is easily certifiable, we always need to consider the worst case. The worst case we found to be human fingers, being a constraint and stationary. That is at least an assumption that the ISO, the standardization allows you, that you can assume the human does not move. That's good. If we would now be able to really predict the motion of the human, if we know where the human actually is, that would give us a great advantage. For example, if we are looking at body parts, like if I would know there is the hand close or there is actually a single finger, that makes a huge difference. According to the evaluations that we've done so far, it would allow us to be by 30% faster in this case. So from 1.2 meters per second, 0.14, here we go, meters per second. We could increase the speed up to 0.2 to 1 meters per second. And this is worst case, having like a sharp geometry in the hand of the robot. If we could say we don't have a stationary motion, but we actually know the motion of the human, we can also consider moving away from a robot. Then we would not have to do any constraint velocities anyway. If we knew what is the difference, like if we have a constrained collision or an unconstrained collision upcoming, then we can also react to this. And there is also a big difference, in this case, even four times almost. This especially that we can say now, okay, we know that if we have a better understanding of the situation and we can actually on the fly assess this situation better, we could actually increase speed and efficiency of the robots by at least 30%. So that's what we see currently, giving a large potential for actually safe and close and efficient interactions for human-robot interaction if we have certifiable human motion detection and prediction. Now, the challenge is, how do we get this certifiable safe? The big point that we are always considering in standardization is that we have this whole constraints on how high can the failure rate be. This kind of breaks down to two components. We look at the software and we look at the hardware. The software is considered to have no random errors currently. There is no random errors currently accepted in software. This is also one reason that you're not allowed to just use any software for programming such applications. You are pretty much restrained to C programming. The software runs on its own hardware. It is decoupled from the rest of the structure. And the systematic errors in the logic are to be prevented by real in-depth documentation. And there is a strict way of how to set up this software structure. The hardware instead, it is allowed to, or that one is the one that is allowed to have this random error. Anyhow, for these robotic applications, we currently have to have it two-channeled, saying that if one channel fails, the second channel can catch still the safety functionality. And now I am here talking to a big group of people that really know a lot about human motion prediction, and probably the best in the world. And none of you will be able to tell me that their prediction has a failure rate of 10 to the -7 or less. You would surprise me if you do. Yeah, that is indeed a problem. So with the current state of the art of certification, we struggle. That is why the ISO is currently having big discussions and technical committees raising more and more to kind of define the restrictions on AI-based software in general. If you want to kind of become part of this and share your knowledge, I guess this is the best time to join currently. A strategy. I am saying it's a strategy because it is obviously not defined yet and it's not safe certified by now. But the strategy is to try to look at the risk again. So we try to reclassify this performance level, this 10 to the -7. Is this really necessary as a failure rate? What do we have to do for that? For that, we have to understand what is the systematic errors that can occur in our prediction and in our detection. Secondly, then we have to understand from this error, what is the consequence? What is the severity that can actually occur if this error is present? So first question is, what is then the question we want to find out is, what is an acceptable remaining risk? For that, we need to know what is the severity of prediction failing, and what is the systematic errors that are there in human motion prediction that we need to consider. Following, I've tried to, from my experience-based view, tried to classify a couple of errors that I've seen, and try to give a bit of an overview of what could be the potential severities of harm arising from them. So one of them is obviously very simple. Human is not detected. Well, that can systematically, or this can be a systematic problem because you have an error in the model, because you have the camera is somehow obscured, you have unexpected behavior that is not covered by the model, for example, and the severity of human presence not being detected at all, well, that's quite high. I don't think we could ever argue to go around performance level D category 3 on this error, because that can lead to a collision. Like if we're considering a humanoid robot today, we've probably all seen these videos of the humanoids currently going a bit rogue, where, well, they are definitely, they will injure a person, definitely. So high severity of harm for this error, and we would probably always need to stick to this performance level D. Anyway, what happens if we do detect the human? That's not the problem. That is safe. We're good with that. But we are predicting and like detecting the wrong body parts. So what might be the errors occurring here? Like this could be because of a detection error, model error again. But the thing is that if we know there's a human, we have already adapted the speed of the robot system, for example. It is the severity that can happen now is way lower. So we are not talking about full speed robot anymore. We're talking about a robot that is already slower. It might still cause more harm to the one body part than to the other, but it is not as bad. Like usually it will always limit to reversible injury. So we actually also have a paper coming up on this injuries, where you can see quite nicely that even if the velocity would not be perfect for the one body part, it would never cause an injury, more severe or irreversible injury in another body part. So this is just medium. We could go down with this performance levels potentially. Positions and distance errors. If the position and the distance is wrongly estimated, but it is still estimated and there is still a human present, so we still can tune down the velocities correctly, well, the risk is rather low, I would say. It's, as I said, from my experience point of view here now. If the situation is wrongly estimated, that once again is a bit more severe, because a constrained human body part takes a lot more damage than an unconstrained human body part in a collision. And so also here, the severity would be medium. You could potentially, you would also have to argue maybe it's still a high severity of harm. So if we are now talking about these severity of harms that are occurring and the systematic errors behind that, we can obviously like assume that this is the severities of harm that we have, but at the same time we can also try to obviously reduce the risk of this systematic errors occurring at all. And here just some examples, some things we've been working on, some inspirations maybe. One part would be to avoid model failure, for example, and prediction failure of the human presence in total. we need to include human errors. We need to include what is the human potentially doing, even like especially if we are looking at close collaborations, things like the expectation of the human for motion of the robot can be considered, because one thing is that if we have an expectation and we know a robot is moving in a certain way, we also adapt our actions to it. And other way around, if I have an expectation, but the robot is not meeting this expectation, there is a likeliness of startle and surprise reactions, how we call it. These can generate involuntary, unpredictable motions. They are very fast. They are hard to consider in the models. And what we have done back in 2022, I think, is we did a study investigating what distances and what velocities are associated to such startle and surprise reactions occurring. So this is one potential way how we could include human errors or human error analysis into the prediction. To prevent things like the misclassification of human fingers and hands and errors or severity of harm occurring from that, what we can do is we can embed safety hierarchies. So we can try to explain that there is always the human finger as being the worst case scenario, constrained human finger. We could allow a velocity of 0.144 meter per second. And even if we have, for example, a low accuracy of our prediction, if we are not as certain about our prediction of the body part, we could still say, okay, we can use this as the safe velocity, because it is the worst case. Other hand, if we know for very sure, if we have a high accuracy in our prediction, we could trust our prediction and we could say, okay, we have a hand and a lower arm, and we can increase the robot speed again. Good. Yeah, so in conclusion, the chances and the value of human motion prediction is very high, especially also in close human-robot interaction. If we are able to really generate certifiable, safe human motion prediction applications, we can gain up to 30% higher velocities, which is quite a bit. But to go into the direction of certifiable, safe human motion prediction, we have to do a very close analysis of what is the errors occurring. We have to define all systematic errors that can happen. We have to assign severities to them. These severities need to be in line with the biomechanical limits of human body parts. We can use all of this knowledge, and we have to embed from the start, while we are already designing the human motion prediction algorithms, applications, whatever. We have to consider this from the start, such that we can, for example, build such hierarchical structures, or we can include into our models unpredicted scenarios, for example. And well, the most important thing I would say is that from our researcher point of view, there is always very few people going into these technical committees of standardization, because it's tough. It's tough. But it's very necessary, and the knowledge sitting here is definitely very valuable. And I would advise all of you, if you want to drive this field a bit further, try to go into these technical committees, try to check out your local standardization committees and get involved. Okay. Thank you very much.
All right, if we have any questions from the audience, now is the time to step up to the mic and ask the questions.
Hello, great. Thank you so much for your talk. I found that really interesting and so important in this field that we have. I was wondering if you can talk at all about how, to what extent you've included people with disabilities, or the idea of that within this. For example, if you have someone who's blind or has a condition where it might be harder to heal from an injury, like what counts as a reversible injury? Just anything in that area. Thank you.
So currently, thank you very much for the question. The thing is, currently we have worked with people that are not alive anymore. So they had everything,
Pretty
literally,
much reversible.
pretty much irreversible. So what we've been really investigating on is injuries that occur. So we have looked at cuts, we have looked at broken bones, we have looked at all of the such. It's not possible to do human studies with living tissue on this part. So what we have done is currently all, well, dead people based. But it is definitely very important to include all of these factors also with the motion prediction. I guess that's makes a big difference, but that's not my field of expertise.
Okay, any more questions to the speaker?
Oh, and thanks for the great presentation. At one point you said, if we knew that the human was moving away, for example, and then I thought, well, that's probably not what you will get from the human motion prediction module, right? So I was wondering to which degree, from your point of view, from the safety point of view, it helps to get, for example, the uncertainties, and in which way you could assess how much gain you get in terms of efficiency, higher velocities, if just the confidence that the algorithm gives you in the different predictions is higher.
That is a very good point also. So the confidence, it's a bit tough to say that again now, but it's kind of like comparing it to this performance level. If we have a confidence that is high enough that we can say, okay, I'm sure that in 10 to the minus 7 cases, it is predicted. Yeah, I know. This is currently completely unfeasible. Anyway, so that is why the thought is going into the direction of redefining these performance levels for such applications. I cannot say now any values or thresholds because there is none currently. But if you are able to really explain why is a certain probability of this prediction being correct, why is this acceptable? Because of a certain injury that we are expecting and because of a certain exposure that we have. If there is no exposure to a human, well, it doesn't matter as well.
Likely.
If there is likely one, yeah, we have to increase the detection likeliness again.
Because the worry is that as long as you say we always have to consider the worst case, and you have just a 0.1% chance that the human is moving towards your robot, then you would always have to keep the velocity low.
Yeah, and that is the current state of the art. So the current state of the art says worst case and nothing else but worst case.
Okay.
Thanks for the great talk. Regarding the safety standards, what we don't certify prediction, but we certify the navigation system, the control system, right? Predictions can be wrong, but then overall, there is some safety mechanisms that protect humans. Would this be still fine for the standards?
The problem here you will face is the software you're running. So there is by now hardware. I'm aware of that there is 2-channeled cameras fulfilling performance level D. This this is there. And with this, what you could currently do is do this speed and separation monitoring. As much as I hate it, it's written in the standards. And you could say, okay, based on a distance, which is quite far actually, that the human has to the robot, I am slowing down because the camera said I am in this area now. That is possible. But that is also, once again, always based on the worst case. And for us, like especially in the close interactions, we are always too close. Like that's not happening actually. So in that field, like in the field of far distance prediction sets, that should be fine. And that is doable. And I probably see that coming within the next years as well, that we have more certified application in this area, but not in the close interaction. So there you still have to.
Seen as a single software.
It has to be fully decoupled from the actual rest of the software running on the robot. So you have to have this C programmed structure of, I cannot tell you right now because I have not ever done it myself yet. I just know the standards, how they describe how this software needs to look like. And this is the essential point. The software has to be safe and there has to be no random errors because of this software.
Thank you.